Hello, this is a movie about Newton's laws of universal gravitation. And let's first start with Kepler's laws. Kepler, he found out by studying the orbits of the planets around the Sun that planets move around the Sun in elliptical orbits with the Sun at one focal point. So each planet moves around the Sun like this, and the Sun is in one of the focal points. Second law, the radius vector drawn from the Sun to a planet sweeps out equal areas in equal time intervals. So when a planet is closer to the Sun, the vector is smaller, but he has to go faster because this surface, let's say we're here in December, then we move from here to here in December, then we move from here to here in July or in June. So this area equals this area, so we go fast here and then slower further on and fast here again and continue like that. Third law, the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. So simple as this is. So orbital period, time for one period, we do that square, it will be proportional to the cube of the semi-major axis. Semi-major axis is this of the elliptical figure. If we do that cubed, then we have a proportional relation. Well, Kepler, he found that planets move around the Sun in these laws, but he did not know why. It took about 50 years or so before Newton came, and he found the law of universal gravitation. In fact, he reinvented it because a few thousand years before, an Indian mathematician had already found the same law. Well, we have here two objects, m1 and m2, mass 1 and mass 2, and they're attracted to each other with the forces F1 and F2. And their distance, the centers of their mass are distant r, are at a distance r. F1 equals F2. Action is reaction, so those two are equal. And it's the big letter G times m1 times m2 divided by r squared. So we take a constant. The constant is this one, 6.67 times 10 to the power minus 11 Newton meters squared divided by kilogram squared. And then we have mass 1, mass 2, and the distance between the two masses in square. Let's see that with a small exercise. Example, calculate the force between the Earth and the Moon at the moment they are closest to each other. 336,295 kilometers. So we have our given here, the mass of the Earth, 5.98 times 10 to the power 24 kilograms. The mass of the Moon, 7.36 times 10 to the power 22 kilograms. And R is 363,295 kilometers. And we are asked to find the force between them. And the solution is F1 equals F2 equals G times M1, M2 divided by R squared, which is our formula. And we just have to fill it in. So we have here our gravitational constant. We have the mass of the Earth, the mass of the Moon, and their distance, the distance between them in square. And we'll calculate that the force of the Earth attracting the Moon, or the Moon attracting the Earth, is 2.22 times 10 to the 22nd power in newtons, of course. Okay, that was it.